So this is continuing lecture 7, periodic trends. So this one I'm going to talk about ionization energy. So again, from the presentations, we have some general trends that we could see. So looking at a real periodic table, as you essentially go down a group, you will see ionization energy gets smaller and smaller. But what the more interesting one is, say for instance that this is, we're looking at period 2 here, starting with lithium, going all the way up to neon there, okay, just focusing on that particular period. You will see as I go from left to right on a periodic table, ionization energy will actually get bigger, okay. So ionization energy is the energy needed to remove an electron. So it should make sense as to why this is the case, okay? But I want to blow up or essentially look at a graph that is looking at the first 20 elements to kind of see some interesting, what I call blips in the actual trend. And again, these are what we call general trends on the periodic table. You will find, if you look at your Flynn periodic table, you will find all kinds of exceptions to the rule. And I will expect you to know a few exceptions. But the one I want you to focus on is boron and oxygen. But we could also look at, say, for instance, aluminum over here. So anytime it kind of dips down. So I'm going from lithium to neon here. I should just see that all of these keep getting bigger and bigger, but I do have what we call exceptions. So let's look at boron first, okay? So if we look at lithium and beryllium, they are filling up the s orbital, and then boron, you start to fill up the p orbital. Okay, you have one electron in the p orbital. So because you have that one electron in that p orbital, it's probably pretty easy to remove it from that partially filled orbital. So therefore, it has a lower energy threshold for that to happen. Then if we look at where oxygen is, okay, oxygen right next to nitrogen, again, this is P1, P2, P3 in terms of electrons in the p orbital. So that's where it's half filled. When I start to fill up the oxygen, the 8th electron, I start to pair them up, okay? So therefore, if I'm looking at oxygen and its p orbital, okay, oxygen's p orbital looks like that, okay? So it is a partially filled, and that one extra electron is making it unstable. If I remove that electron, it then becomes half filled, and that's far more stable. So that is why you see a blip down with oxygen below where nitrogen is, because of that half filled orbital phenomenon. If you go to aluminum, okay, it is right below boron, okay, so it has that, you're starting to fill that p orbital, so that's why it is there. And then sulfur kind of follows with what oxygen does. You start to see the further and further down you get in those groups, you don't see as big of an exception to the rule. So a couple other exceptions that you can put in your notes, and again, I'm going to expect you to know these exceptions. Gallium versus aluminum, again, think of the fact that gallium is a smaller atom due to, again, the D not being a good shielder. So it's going to be much harder to remove an electron. So therefore, it's going to require more energy, not a huge amount, but it does have, it is a blip in terms of the exception. And then TL versus IN. TL is thallium and indium, okay? They're in the same grouping, okay, right underneath gallium and aluminum. So again, I start to fill in the F orbital with thallium. So that is going to be even a worse shielder than the D orbital. So therefore, it's going to be a much smaller atom. And so therefore, it's going to require more energy for that to happen, okay? All right. Then the only other thing I want to mention with ionization energy is we have ionization energy. We mostly focus on what we call the first electron to be removed, but you can remove more than one electron in an atom, okay? So I like this table because it has this dividing line that shows you where you start to see more and more energy being used. So IE1 is the first electron to come off, IE2 is the second electron to come off, and then this is the third. And again, all of this is energy. And this happens to be, I think, in kilojoules. It doesn't really matter what unit it happens to be in. But if I think of where things are on the periodic table, okay, sodium is in that first column, okay? It's going to be a +1 ion when it becomes an ion, okay? Well, the next door neighbor is magnesium, okay? That's going to be a +2. And then aluminum is going to be a +3. Well, can you use this data and support those ions? Well, if I look at sodium, it releases 1 electron with 498. But then when I try to release a second electron, it's going to be 4,560. So obviously there's a huge jump between the first electron to come off versus the second. While magnesium, the first and the second are here, but then there's a huge jump here if I want to remove 3. Well, aluminum wants to remove 3, but boy, it does not want to remove 4. So all I like about this data is, can you look at data and essentially support your claim of what the trend happens to be or what phenomenon you are looking at. So that's why I like that table. Okay. All right, so. All right, so the next trend is what we call electron affinity. And this one I think is probably the most complex of the ones, mainly because we never really touched on it first year chemistry, so it's far different than what we've seen before. But electron affinity is essentially kind of the opposite of ionization energy, where you are trying to put in an electron and whether or not something wants an electron or not. So I like this graph, and again, sometimes you will see different graphs depending upon the book. But what I want you to focus on is the fact that these are negative values as you go up here. So you will see the halogens, the fluorine, chlorine, bromine, iodine. And as you go down that group, you should see somewhat of a trend, but chlorine's kind of an outlier. And then you're going to see some things down here that are below 0, okay? And these are, again, mostly noble gases, but we do have some other ones that are below 0. So we need to kind of define what does negative mean and what does positive mean. And do realize that in different books, they do this slightly different, which is kind of confusing. So if I have a negative value for electron affinity, which is most of the things that are above 0 on this chart here, what you're saying is I'm adding an electron and making it a negative ion. So there's definitely ones that want to take on electrons and ones that don't. But what the negative means is, like we saw with thermo, is energy is being released. Energy is being released, okay? If I add an electron to something that has what we call a positive value or something less than 0 on this particular graph, meaning it's positive, it is going to be what we call unfavorable, okay? Endothermic-ish, meaning I need to add energy to it in order for this to happen. So again, that's not going to be very favorable when we look at different situations. So again, the noble gases are all going to be what we call, I don't know if I would call it an exception, or the ones that are going to be positive. Negatives are going to be, again, the more negative it is, the more likely it wants to take on electrons. So take on, again, your halogens. For those are going to be those things. Again, they want one more electron, and then they would be happy with that. So the exceptions I do want to talk about are nitrogen is greater than 0. It is not a noble gas, but because of the fact that it has that half-filled orbital, that p orbital has 3 electrons in it. It is half-filled. That is a very stable configuration. So because of that, I'm going to need to put energy in order to take that electron in. Okay. Another one happens to be beryllium. Okay. Now again, beryllium has 2 electrons in the 2s. Where it's located, so it has a filled s orbital. So it doesn't really want to put another electron in. It can, there's a p orbital, but it doesn't really want to do that. And since it's relatively small, that's why you see a bigger exception here than anything else, okay? Again, if you want to do other exceptions here, again, there's magnesium and some other ones along the way. You can use those, but I kind of like those because those are pretty simple and easy to remember. And then finally, the last trend we have is something called electronegativity. And we're going to really focus more on electronegativity when it comes to bonding. And again, some groups might have spent some time on bonding for electronegativity. So we're going to come back to that very strongly in Chapter 8 and Chapter 9. But I still like to do electronegativity as a trend. Do note that fluorine, it's not a very good copy here, has the highest value here of 4. This is called the Pauling scale. And the Pauling scale is essentially, the scientists figured out, well, if you have these two atoms in a bond, who is more likely to take on the electrons, or the electrons being closer to them? So fluorine is the most electronegative element. So if you remember that, you could kind of compare things that are next to it. So as you go from left to right, it increases. As you go down, it decreases. And again, a lot of these trends, I'm going to just ask some simple, straightforward questions. This one in particular, I'm just going to ask you to compare things and say who is more electronegative and who isn't. But I did put in your notes some general trends for what you see on electronegativity. And electronegativity does give you information on what we call the oxidation states that we talked about when we were balancing oxidation reactions. And it does tell you where the electron density is shifting in that bond. So it is going to be something we see when we get into making bonds themselves. So again, some of the presentations we might have seen talked about, again, polar versus non-polar and ionic. Again, we are pretty much going to not have any numbers that we could reassociate to say that's polar or non-polar. So again, it's going to have to do with what we call degree of ionic character. That's really what we're going to focus on in AP Chem rather than a number to say if it's polar or not.